So today we're going to consider another probability problem. Probabilities involving single-stage experiments are easy enough because only one thing is happening to affect the probability. For example, we can flip a coin once, we could pick one person at random, or we can pull a card out of a deck. Probabilities, both empirical and theoretical, become increasingly more complicated with multi-stage experiments. When more than one thing happens, like flipping a coin 3 times, or tossing 2 dice, or even 3 dice. So let's consider this do now problem. Suppose we toss a green and red die, and we record the numbers in the experiment. Find the probability that they show a sum of 4. Well, in a problem like this, we could actually count which outcomes would show a sum of 4. Okay, so if we agree that the green die is first and the red die is second in the ordered pair, we could have outcomes like 1, 3. That's a sum of 4. 1 on the green, 3 on the red. We could have 3, 1, which is 3 on the green, 1 on the red. And we could have 2, 2. The question is, how many possible outcomes are there? Well, in our previous video, we know that there's 6 possible outcomes for the first green die and 6 possible outcomes for the red die, and by the counting principle, there are 36 outcomes. So we have 3 possibilities here out of 36. So the probability that they show a sum of 4 is 3 out of 36. Okay, notice that each of these outcomes are equally likely. The probability of each of these outcomes is 1 out of 36. However, the probability of a sum is not equally likely. So before we answer the other questions, let's list the outcomes in the sample space. Okay, so we'll do that in a dot diagram. So we'll make a dot diagram, and this first one is green, and the second axis is red, and we'll list them here. And 1, 2, 3, 4, 5, 6. Okay, so I'm going to put dots at every point, and this outcome would represent 1 on the green, 1 on the red. This one would be 2 on the green, 1 on the red. This would be 3 on the green, 1 on the red, and 4, 1, 5, 1, and finally 6, 1. So I'd like you to fill in the outcome set. Pause and let's fill this in quickly. So we have a picture of the outcome set, and we've listed all 36 outcomes as ordered pairs. And if we wanted to get the probability, okay, let's just try to write this out now. So if we wanted to get the probability that the sum is well, let's look at all the sums. The minimum sum is 2, and the maximum sum would be 12. So a sum of 3, a sum of 4, a sum of 5, a sum of 6, a sum of 7, sum of 8, sum of 9, and sum of 10. And we see a pattern emerging in the sample space when we list it in a table format the way we've done here. Okay, so let's circle. The outcome for sum of 2 is just 1. It's 1, 1. So that's 1 out of 36. A sum of 3, we already have a 1, 2 and a 2, 1, and that would be 2 out of 36. A sum of 4, we've already listed, they're here. And we have 3 out of 36. So I'd like you to take a minute and fill in the rest. So a sum of 5 is located on the next diagonal, which gives us 1, 2, 3, 4 outcomes. That's 4 out of 36. A sum of 6 would be the next diagonal, so we have 1, 2, 3, 4, 5 out of 36. A sum of 7 would be the next diagonal, so we see a pattern emerging here. That's 1, 2, 3, 4, 5, 6 out of 36. A sum of 8 would be here. Then we're down to 5 out of 36. And notice the symmetry here. 1, 2, 3, 4, 5, 6, 5. What do you think the sum of 9 would be? Well, my guess would have been 4 out of 36. Let's just verify it. 1. Yes. Sum of 10 would be, I would think 3 out of 36. 1, 2, 3. There we go. And the probability of a sum of 11 are 2 ways, which is just 5, 6, and 6, 5. And the probability of a sum of 12 would be 1 way, 6, 6, which is 1 out of 36. So there is a definite symmetry here in the chart. Notice that the probability of the sums are not equally likely. The probability of each outcome is equally likely. And if we added all these fractions that we have on the right-hand side, we would get 36 out of 36. The sum of all the simple probabilities should be 1. So let's take a look at another two problems that I wanted to bring to your attention. The probability that the sum is less than 12 and the probability that the sum is more than 4. Okay, before we begin, if we go back to the do now and add up all the probabilities of a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the probability of all of those sums is 36 out of 36 if we added them. And I'll leave that up to you. So sometimes it's useful to look at the event, the opposite event. For instance, the opposite of the event of a sum less than 12 would be the probability that the sum is more than or equal to 12. And subtract that from the probability that the event must occur, which is 1. Okay, so let's think about this. Here, the maximum sum of rolling two six-sided die, is 12. So the answer is that the sum that's equal to 12 is 6, 6, which is 1 out of 36. The sum cannot be more than 12. And subtract it from 1, and we get 35 over 36. This is called the complementary event. So if E is the event, the complementary event is denoted with a bar over the E. And so the probability of E can be found by taking 1 minus the probability of the complement. And that's only true if the complement doesn't have too many outcomes. I mean, that's when it's useful to do it. So I'd like you to try B the same way. All right, pause and try it. Okay, so I've done it for you. The complement of a sum more than 4 is the sum less than or equal to 4. And those are pretty easy to list. 1, 1, 1, 2, 2, 1, 1, 3, 3, 1, 2, 2. And there's 6 possibilities there. So it's 1 minus 6 out of 36. So the answer is 30 out of 36. So I just wanted you to be aware that sometimes it's more useful or easier to look at the complementary event when finding a probability. And the complementary event can be illustrated with number 4. Suppose we roll 3 dice. Okay, so let's think about it. If we roll 3 dice, the maximum sum that could occur would be having a 6 on all 3. So the maximum sum is 18. Okay, so that's only one way it can occur. But if we want to find, and the probability of rolling the maximum of 18 would be 1 over, and using the counting principle, the number of elements in the outcome set would be 6 for the first, 6 for the second, 6 for the third, and we multiply. So the answer would be 1 out of 216. That would be the probability of a sum exactly equal to 18. But if we want the probability that the sum is less than 17, well, let's think about this. This would be equal to 1 minus the probability that the sum is more than or equal to 17. So I will leave that up to you. Pause and figure that one out. Now, the outcome set for sum more than or equal to 17 is not so hard to list. Let's think about this. We've got 666. We've got 665. We've got 566, and we've got 656. And because we have to use a 6 and a 5, there aren't too many outcomes. And we see that there are 4 possible outcomes for a sum more than or equal to 17. So this would be 1 minus 4 over 216. And the answer here would be 212 over 216, which would be very difficult to count if we listed all the possible outcomes. So here the complementary event is very, very helpful. So this is a question to think about. We saw that when we rolled 2 dice, the sum that was most frequent was a sum of 7. What do you think would be more frequent? What sum would be most frequent when we roll 3 dice? That one I'd like you to think about. So we will conclude the lesson with this last problem. Suppose we put the numbers 1 through 7 in a hat, and we ask Benson to pick a number from the hat. And then we have the numbers 1 to 5, we put those in a hat, and Katya picks a number from the hat. Let's list all the possible ordered pairs that can occur, with the understanding that the first number is what Benson picked, and the second number is what Katya picked. Okay, let's try it. And then, once we list our outcomes, we'd like to investigate B, the probability that the sum of the outcomes are even. C, the probability that we have a double. And D, the probability that the sum is divisible by 2 or by 3. Notice that if the sum is divisible by 2, it's equivalent to saying that the sum is even. So parts B and D are overlap. Okay, so try this by yourselves. Pause the video and we'll continue. Okay, so of course in this problem I did forget to mention that the probability for Benson to pick a number from the hat 1 through 7 are all equally likely outcomes, and the same is true for Katya. So by the counting principle, there are 7 possible ways Benson could pick a number, and Katya has 5 possible ways. So the total number of outcomes by the counting principle would be 7 times 5, which is 35. So each of these ordered pairs that are listed have a probability individually of 1 out of 35. Notice that 2-3 is different from 3-2. 2-3 would represent that Benson got a 2 and Katya picked a 3, whereas 3-2 would mean that Benson picked a 3 and Katya picked a 2. So order does matter, and we have 35 possibilities. So let's just label this side here, 2, 3, 4, 5. And the probability that the sum is even, well, we could count those. The probability that the sum is even, the sum could be a 2, a 4, a 6, an 8, a 10, or a 12. These are all possible sums, and the maximum sum is 12 because the last ordered pair here is 7, 5. So let's look at it. The sum of 2 is, of course, 1, 1. The sum of 4, if you look carefully, is along this diagonal. That's a sum of 4. A sum of 6 is along this diagonal. These are all sums of 6s. Oh, let me see if I could try to include all of these points. Okay. The sum of 8, again, is a diagonal, and the 8 is here. The sum of 10 is this diagonal. And of course, the sum of 12 is just this point. So notice that 7, 5 and 1, 1 are equally likely. They're 1 out of 35. Whereas the others we have to count. And if we have a list of all the outcomes, it's so much easier to count them. So for sum of 2, there was one possible way. A sum of 4 are 3. Sum of 6 is 1, 2, 3, 4, 5 ways. A sum of 8 is 1, 2, 3, 4. 1, 2, 3, 4, 5 ways again. A sum of 10 is 3, and a sum of 12 is 1. So when we add these all together, what do we get? 10 and 8. I guess the answer would be 18 out of 35 would be the probability. Now, the probability of a double, well, the doubles are easy to count. We've got 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5, and that's it. We can't have a 6, 6, or 6, 7, so that would be 5 out of 35. And I'll just list them here. 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. These would be the outcomes that would satisfy that event. Now, the probability that the sum is divisible by 2 or 3 is a little more complicated. We have to see the probability that the sum is divisible by 2, which we already did in part B. That was 18 out of 35. Plus the probability that the sum is divisible by 3. Okay, that one we'll figure out. Minus the probability of the sum divisible by 2 and 3. Means that the sum is divisible by 6. And I think that would come right out if we list the possibilities. So I've circled in red the sums divisible by 2. Let's circle in blue the sums divisible by 3. Okay, so what are the ones divisible by 3? Well, let's see, we'll circle them. 1, 1 is out. We have 1, 2, and 2, 1. That's a sum divisible by 3, which is divisible by 3. The sum is 3. We could have a sum that's 6. So let's see. This diagonal doesn't match. This is a sum divisible by 4. No. The next diagonal is a sum divisible by 5. No. But the next diagonal is a sum divisible by 6. So this is where we will have our overlap. We can see that we have an overlap. The sum divisible by 9, well, the next one is divisible by 7. The next diagonal is divisible by 8. So this diagonal is divisible by 9. Or is 9. The sum is 9, which is divisible by 3. The next is divisible by 10. The next one's divisible by 11. But the next one's divisible by 12. So we've got that. So whatever is outlined in blue is divisible by 3. So let's count them. So divisible by 3, okay, divisible by 3. We've got 3 out, let's see, divisible by 3. We've got, so let's put a 2 here. That's a 1, 2, and 2, 1. Divisible by 6, well, there is 1, 2, 3, 4, 5 outcomes. And divisible by 9, 1, 2, 3, 4 outcomes. And divisible by 12, we've got 1 outcome. So if we add those all together, we get 7 and 4 is 11 and 1 is 12. So the probability here is 12 out of 35. But notice that our markers overlapped when we have a sum divisible by 6. So we have to subtract here the overlap, which is 5. So the final answer would be 18 plus 12 is 30, minus 5 is 25 out of 35. And I hope we did that correctly. Because of the overlap, we counted this twice. So we would have to subtract the 5. So that would be essentially adding 7 more, which would be 25 out of 35, and that is correct. So that concludes our lesson with the dice problem, or with a problem that has 2 possible outcomes. And in problems like these, note that each individual outcome was equally likely, but their sums were not. So we have to be really careful. And that takes care of our lesson today. Have a wonderful day, everybody. Bye.